All right, guys, before we get started, any questions over the homework assignments? Did everybody get the AMI sheet from in here?
You know what, how about this? Do you have any questions about my homework assignments?
You haven't done?
Actually, yeah, I have one.
If you have it here, I'll take it.
Sorry.
Yep. What we're doing today is more simplifying these rational exponents and radicals, mainly focusing on rational expressions. Today we'll focus more on radicals later. And what we have here are properties of powers, properties of exponents. And most of these we've already done. You all have worked with before. You have used these before. So product of a power, if we multiply like bases together, we add the exponents. Power of a power, if we have a term to a power, we multiply the powers. Power of a product, two things multiplied together to a power, we can apply that power to both terms. Negative exponent, if the exponent's negative, we can move it from the top of the fraction to the bottom, or bottom to the top. Zero exponent, a to the zero, anything to the zero power is 1 except for 0. 0 to the 0 power is not going to be 1. Quotient of powers, a to the m over a to the n. If we divide like bases, we subtract the exponents. And lastly, power of a quotient, if we have...
Fourth-hour class needs to go down to her classroom and pick up their AMI work.
Two terms being divided to a power, we can apply that power to both terms. We've done these, we've dealt with these. And we can also use these for simplifying radical or radicands. So, no radicands have perfect nth powers as factors other than 1. All that's saying is that we can't leave something as, say, the square root of 16. If we can simplify it, we need to simplify it. Square root of 16 makes sense because square root of 16 is 4. Although if we had the cube root of 16, we have to go through the process of simplifying it down to 2 cubed roots of 2. If it can reduce, we need to reduce it. No radicands or radicals can contain fractions. We can't have the square root or a fraction inside a radical. And no radicals can appear in the denominator of a fraction.
Sorry.
All right. So what we're doing today is simplifying these expressions using our properties of radicals, or our properties of powers. So the first one we have 7 to the 1/4 times 7 to the 1/2. Well, because we can try plugging 7 to the 1/4 times 7 to the 1/2, like that, times 7 to the 1/2, and we get this ugly decimal, and that's not going to be the answer that we want. We want to simplify it. Now, according to our product of a power, when we multiply like bases, we add the exponents. So 7 to the 1/4 times 7 to the 1/2 is the same as saying 7 to the 1/4 plus 1/2. When we multiply like bases, we add the exponents. So now the next thing we need to do is add 1/4 and 1/2. Now the calculator can do this for us, because if we are going to do this by hand, we would have to get the bases to be the same. So we'd have to rewrite them both as fourths, telling us that 7 to the 1/4 times 7 to the 1/2 is 7 to the 3/4. 6 to the 1/2 times 6 to the 1/3. Well, the bases aren't the same, so we can't use our product of a power, but we do have a power of a product. We do have two things multiplied together that are being put to an exponent. So we could say that this is the same as 6 to the 1/2 for the second times our 4 to the 1/3, guys, to the second power. Now powers of powers multiply. So we have our first one is 6 to the 1/2 times 2, and that's being multiplied by our 4 to the 1/3 times 2. Now with our 6, we have 1/2 times 2. What is 1/2 times 2? 1. So we can just say 6 to the first, or just 6. With our 4, we have 1/3 times 2. 1/3 times 2 is 2. That's it. There's nothing we can simplify from here. 6 is already as simplified as it gets. 4 to the 2/3 doesn't reduce any further than what it is. Because even with 4, 4 is 2 squared, but that's not going to help us reduce the denominator of that exponent. Questions on A or B? Now we can treat C the exact same way we just did B, because we do have a power of a product. So we can multiply here, telling us that we have 4 to the 5 times negative 1/5 times 3 to the 5 times negative 1/5. Questions on this so far? 5 times negative 1/5 is what? 5 times negative 1/5? Well, the 5 would multiply with the negative 1 and give us what? Negative 5. And it'd be over 5. Well, what is negative 5 divided by 5? Negative 1. Well, we'd have the same thing for 3, really telling us that we have 4 to the negative 1 times 3 to the negative 1. Well, to make the 4's exponent positive, we would take it from the top of the fraction to the, and we'd have to do the same thing for 3. Which tells us that we have 1 over 4 times 3. Well, what is 4 times 3? So 4 to the 5th times 3 to the 5th, all to the negative 1/5 is 1/12. But again, with any of these here, we're taking it one step at a time, using these properties to simplify it. We do have a fraction. We don't have any rational or fractional exponents in the bottom of this fraction, so that tells us that it is simplified there. We can have fractional exponents in the top. That's fine. And nothing is reducible. We can't get it any smaller than what it is. Questions on this here? D, 5 over 5 to the 1/3. Well, we have two numbers, our 5 and 5 to the 1/3 being divided. When we divide like bases, we do what? Subtract the exponents. So we can rewrite this as 5 to the something minus 1/3. Well, what's the exponent on top? 1. So we're saying that 5 over 5 to the 1/3 is the same as saying 5 to the 1 minus 1/3. What is 1 minus 1/3? Five is a prime number, so there's really no way to reduce this any further than what it is. So it's 5 to the 2/3. If our base is not a prime number, we might have to check and make sure nothing reduces. So like taking the cubed root of 8, 1/3, 8 to the 1/3 is the cubed root. We're trying to find what times itself 3 times. I can't just leave it as 8 to the 1/3. It's not reduced. Or 4 to the 1/2. If we can reduce it, we need to reduce it. Questions on this so far? E, 42 to the 1/3 over 6 to the 1/3 squared. Well, as we used just a minute ago, our quotient of powers, a to the m over a to the n, is equal to a to the m minus n. We could use that on D because the bases are the same. E, the bases are not the same, so we can't just do that property. But 42 and 6 do both have the same exponent, yes? Is 42 divisible by 6, or do they have something in common? So 2, yes? Now 42 and 6 are both divisible by 2. Actually, 42 is divisible by 6, yes? So it'd be nice if we can get rid of that 1/3, because I can't just do 42 to the 1/3 divided by 6 to the 1/3 and get 7, because of that power, yes? Power of a quotient says what? A over b to the m is equal to a to the m over b to the m, yes? Well, we can actually use this in reverse, because we're used to saying a over b to the m is a to the m over b to the m. We're used to applying it that way. But there's nothing that says that we can't go the other direction, because they are equal. So I can take that 1/3 power and put it back up as an exponent. So we have 42 over 6 to the 1/3. And the reason that this is nice is because I couldn't just directly divide 42 to the 1/3 over 6 to the 1/3. I pull that exponent out. Now inside we have 42 over 6, which we know is 7. So it gave us a way to simplify this nicer, or a little bit easier than just trying to work it as it was. we're able to get rid of 6, which we couldn't take 1/3, or the third root of 6, or the third root of 42. Powers of powers do what? Multiply. So 1/3 times 2 is 7 is a prime number, so we're done. Because really this whole lesson today is just we're looking at these properties of exponents and utilizing them to get this in a simpler form, in a nicer form. Yes. Yeah. Empty carbs. Number 1, 2 to the 3/4 times 2 to the 1/2. We're multiplying like bases, so we can do what? Add the exponents. 2 to the 3/4 plus 1/2. 3/4 plus 1/2 is 5/4. 2 is prime. 2 is a prime number, so we can't reduce that fraction at all. We can't make it any simpler, any nicer. The only times we possibly can is when we start getting our perfect squares. 4, 9, 16, 25, 36, 49 cubics. That's as simplified as it gets. Number 2, 3 over 3 to the 1/4. We're dividing like bases, so we can subtract the exponents. The exponent on top is 1. The exponent on bottom is 1/4. So we're doing 1 minus 1/4, which is 3/4. So 3 to the 3/4. Number 3, 20 to the 1/2 over 5 to the 1/2, all to the third power. $20 and 5, are they divisible? Can we simplify that? 20 is divisible by 5, yes? So we can pull that power out. Tell us that we have 20 over 5 to the 1/2 to the third. 20 divided by 5 is 4. Because again, the reason we're doing this step or doing it this way is we want to get that 5 to the 1/2. We don't want that fractional exponent in the bottom of the fraction. This is the first one where we've got a number that's not a prime. 4 is not prime. What is 4? Well, 4 is what? 2 squared. And the reason I bring that up is because 1/2 is the same as our square root. 1/2, we're trying to see what times itself is that number. Well, what times itself is 4? 2. So if we did this multiplication here, because we'd have 2 times 1/2 times 3, well, 2 times 1/2 is what? 2 times 1/2 is 1, yes? Because if you have 2 halves, it makes a whole. And 2 to the third is 8. So really, if we wanted to, 20 to the 1/2 over 5 to the 1/2 to the third, 20 to the 1/2 over 5 1/2 to the third power. Would have told us that it is 8. But this is one of the few that we've done. Yeah. That we could have typed it in. But most of the ones on this section, we're going to actually have to work out by hand to get the answer. Number 4 is our power of a product. So we can apply this third power to both. Telling us that we have 5 to the 1/3 times 3 times 7 to the 1/4 times 3 well, 1/3 times 3 is 1, just giving us 5. 1/4 times 3 is 3/4. Telling us that we have 5 times 7 to the 3/4. And that's it. Questions on this here? Questions on anything we've done so far? We feel comfortable with these here. All right. And that's it.